gonna code clip today. Yesterday, I drafted it on my iPad. The video's up. So we're gonna code clip. We're gonna just jump right into it. I don't think I want to do any preamble. I said everything I needed to say yesterday. So we're going to I'm gonna code it up from scratch in PyTorch, and then I'm gonna do a training run and show you that essentially the model doesn't really learn anything, just given the data set we're using, Flickr 30K. Okay, so this is just a quick edit I wanted to insert. I realized in the intro I didn't explain this fully, but so this video, I actually ended up changing it kind of partway through. I was gonna code the clip architecture and the training run in one go, but it ended up being a lot more than I thought. So I only coded the clip architecture, and then I stopped the video, and I'm gonna upload that. Also, the reason why clip doesn't converge, even though I'm not showing it in this video, but the reason why clip doesn't converge is because I'm training it on the Flickr 30K dataset, which isn't enough for the transformer architecture, right? Like, this model was originally trained on 4 billion data points, the Lion dataset. So transformers are data hungry, and Flickr 30K isn't enough to actually show convergence. But the model, it is the correct model, and you will learn exactly how clip works in and out from scratch by watching this video. So I don't want that comment of, oh, it didn't converge, to throw you off. That's why. And in the next video, I'm going to do an actual training run and explain more why it doesn't converge, but also kind of show you how you can sort of debug something. So anyways, back to the video. And right, so let's get into it. I think so. I guess in the description it's in the README for the repository, I can describe how to get the data. So okay. I have, just to save time, right? I have the basic scaffolding set up. So I'm gonna code the training loop. I'm gonna code the transformer from scratch, clip, and then I'll build that all the way up to clip. So the vision encoder, the text encoder, the loss function, and then I'll code the training loop and the data set. It needs a custom PyTorch data set and a batch collator. So basically how to collate the batch. So the rest will be scaffolding. Like, I already have the import set up and stuff. Like, I don't want to work my way through that. Also utility functions, like, I don't know, just the way we've been reading from the config files. I already have the config file set up. I'm not going to code those. I don't know. I just need to save time because these videos are already long enough. So anything else? No, I think that's it. So maybe I'll break out. You know what? Maybe I should get the notes from my iPad. And then we can reference these notes. We can reference these notes on the fly just to sort of, show how you can, you can just look at the diagram, right? And then code, use your understanding of PyTorch to create from this diagram. But I'll refer to it sort of after the fact, because I already know how to code transformers from memory. So okay. Also, another thing to note is I created a diffusion project, and it's gonna house like a transformer package, a clip package, autoencoder package, right? To have all of these various components, these modules that I've been coding over the past few months. So this training script is going to be a bit more modularized than what you've seen before. And it'll make it a little shorter and just a little bit easier to read, easier to navigate. So, okay, anyways, let's get started. So we have this. Okay, so we have the diffusion package, and then underneath that is clip tokenizers, transformers. So under clip, we're going to have this train.py, which is right here. And that's going to be our training script. And we're going to call, in our training script here, we're going to create a new model, and it's going to be clip, right? So, and that's going to come from, we're going to import it from this clip package here, model. And then models is going to refer to transformers. So let's do like a bottom-up approach. So let's start coding the transformer modules first. Yeah, okay. I don't like that name, transformer modules. I can do better. But we'll just leave it there. We'll leave it there for now. All right, okay. So we'll do patch embedding, class patch embedding. We'll leave that there for now. Forward, say return X. Okay, the patch embedding. You know what? I think okay. So the patch embedding is going to be. So we need to create the patches. So we'll have and then a class token, and then a positional embedding, and then dropout. Right, so it's going to be and then we're going to broadcast a class token, and then add the positional embedding. And then we're gonna do dropout before we return it. So patch embedding, remember, this is the neural network. So let's see. In channels is going to be in channels. Actually, it's just in channels. And then the out channels is going to be, the embedding dimension. So, okay, let's make it easier. I can do this from memory, but I think for those of you who are following along, it'll be easier to look at the diagram just to get an intuitive sense of what we're going to do before I actually start coding. I think that'll be. I would like to see that if I was watching this video. So okay, how do I? Okay, so we have this convolution, this conv2D. So we need to use this convolutional layer to extract patches, right, of size D, P patches of size D, right? So first we have our, input tensor of batch B by C by H by W, and we need to turn it into this. So I'm not going to go over that now. You can watch the last video, but we're going to run it through the convolutional layer, flatten it, transpose it, and then and flatten it and then transpose it. That'll give us our patch embedding before we add the rest of the stuff, right? So image size, in channels, embed dimension is going to be a dropout. And then it's going to be a patch size. So in channels is going to be 3. Out channels is going to be embed dim. And then kernel size is going to be patch size. And the stride is going to be patch size, just like in the notes. Kernel size, patch size, stride, patch size. So you can see just right here what's happening. Class token, remember, it's gonna be a single token that we're gonna broadcast, right? It's of size, it's a single, so the batch is just gonna have one class. Each batch is gonna have one. I mean, the whole entire model has one class token that learns how to aggregate information, right? So it's gonna be, it's a parameter, right? And we're gonna initialize it to be zeros. They're not exactly 0, right? They're numbers that are very close to 0. And it's going to be of size 1, 1. So the batch dimension is 1. And then, we're adding it to, right, a size, number of patches, and right, so sorry, we don't care about the number of patches. It's only 1 here, so it's another 1, and then it's going to be of size embed dim, which is, right, we're going to initialize that to be 512, so we can say that. We can say patch size is 32, dropout is 0.1. Positional embedding is another parameter. So looking at this diagram, right, we're just going to add this. We're going to add this positional embedding as like an offset, right? It's like a learnable offset. So that's of size 1. P is going to be equal to, so the number of patches is going to be equal to the image size in an integer division patch size. So it's going to be P, right? And then plus 1, because we now have the class token appended at this point, and then embed dim. And that gives us this. Something that we can add to this. It's the same dimensions. And then dropout. Let's actually, okay, no, I'll do that next. Okay. So now we're gonna come down to the 4. We're gonna broadcast the token. So we need to concatenate. We need to broadcast. We need to append it to the beginning of each. We need to append the class token to the beginning of each embedding in the batch. So torch.cat. So first let's do B, C, H, W, okay. So that's our input image. And then we're gonna append self.class token.expand. So this is how we broadcast it. So we need to essentially expand the first dimension, right? So this is this is 1, 1, D. So we'll say D. Okay. This is 1. Right, this is B. Actually, you know what? That might make things more confusing. So we're going to expand the class token to b, -1, and the rest of the dimensions, we're going to let PyTorch naturally, fill out the remaining dimensions, right? It'll leave the rest of the dimensions the same, right? But the b is what the dimension we want to broadcast across. So we'll append that to x, and then that's going to be on the first index. So that's on the patch level. So right now, this is going to be b by p plus. Actually, so let's back up. Well, by now it'll be p plus 1, but I forgot I need to do some operations first. So remember, I need to do, after I send it through the convolutional layer, I need to flatten it and transpose it. So right now, we have, after the convolutional layer, we have b, d, h divided by patch size, w divided by patch size. Okay, so now we need to say x equals x dot flatten. We're going to flatten starting at this dimension, so 2, which is going to multiply. That's going to create a vector with these two multiplied. And then we're going to, actually, I'll spell it out. I'll spell it out and then I'll condense it. B, D, P, where P equals H divided by PS times W divided by PS, right? And then we're going to say X dot transpose 1 and 2. So we're going to transpose these two dimensions, which is going to give us something that's starting to look almost exactly like the patch and the final embedding we want to return from this layer. So now we append the class token. We get p plus 1, right? We broadcast that token across the entire batch, and then we're going to add the positional embedding. So x receives x plus self dot positional embedding. Boom. And then we send it through dropout. So now what I wanted to do, let's say, now I want to test that. I just want to make sure the shape looks okay, which I mean, I'm pretty sure this is going to work. 3, 224, 224. All the defaults should be okay. This is the channel dimension. These are the image size. Line 20. Oh, sheesh. I forgot to square this. Okay. That took way longer than I wanted it to. All right, so we have our patch embedding. This looks correct. 10 by 50 by 512. So let's make the attention head now. The attention head is going to have query key value I think that's it. Drop out. It's going to be embed dim to head size because we're doing multi-head attention. So it's going to split head size. So embed dim head size. P drop out. Okay. Boom. Okay, so this. Remember, multi-head attention is going to split our token embedding, our patch embedding, or token embedding along the last dimension, right? Along that embedding dimension. So we're going to have to divide D by the number of heads, which gives us head size, right? And then we're going to do calculate our attention with the mask, softmax, then calculate value, multiply by the value matrix, drop out, and then X, right? So, and return X. So this is going to be Q value so first of all, B, so be B, T, D, so A times, so now we have to scale by the head size. Raise that to the power of -0.5. Okay, now we have to apply an attention mask. Like I explained in the last video, we don't want to calculate attention on padding. So mask is not none. So we're going to pass this attention mask in as zeros as a tensor of size mass.shape is going to be the token, or B by T. Right. Where instead of an embedding in the at each index in the token, it's going to be a 0 or 1 if there's a if it's padding or not. So we need to convert this to Boolean, and then add an extra dimension. So like this. And then we need to do attention. So we need to not where the pad mask is false. Wherever the pad mask is false, we need to say, we need to make it a float of 1 over E, 1 over right, 1 over yeah, that's right. Of a large negative number, so that E raised to the power of that number, so it'll be 1 over E to a large negative number, which will make the softmax 0. So now we're going to do along the last dimension, right? So that'll be row-wise normalization, and then no, then we do dropout. Also, last edit, this, I think maybe I just copied and pasted or something. It's supposed to be dropout in the attention. And then we pretty sure this is right. I said that last time, and then, but pretty sure this is right. So the number of tokens is going to be, let's say 10, let's say 7, and then embedding of size. Well, sorry, this is just B. T equals 7, and size equals channels equals J, number of tokens, attention, head size will be 8. Let's make it explicit. Then will be 512. P dropout. Line 36. Oh, wait a minute. Yeah. This is b times, it's gonna, these are, we'll already have, by the time it gets to an attention head, we will have already gotten the token embedding. So this will be b times t times d. But self is 3D. Oh, this is transpose. This is a three-dimensional tensor, so I can't just do call t. It expects a two-dimensional. So I'm going to transpose along. I'm going to transpose 0, 1, and 2. So it'll be bt times h times bh times t. Actually, I should, you know, do this like I usually do, right? It helps. So b t h. B, this is going to be b t t, so we're doing bth times bht. This is going to be b t t t t t b t h. So it's btt times bth, which is bth. Yep, size 8. The last dimension looks good. This looks good. So now we're going to code multi-head attention. That's just going to, you know, create several attention heads, send the data points through, and concatenate them, project them back into the embedding space, right? And then call dropout. So I know it's going to need that. It's going to be number of heads, p dropout. I think that's actually all the fields we need. Head size is going to be embed in heads, right? And then attention heads, it's going to be module list. Attention head. Head size, embed dim, p dropout. For blank in range, and heads. Boom. First of all, okay, call the super constructor, and then we need a projection layer. So it's gonna, it knows how to take the concatenated embedding and reform a sentence embedding, right? Put it back into the same embedding space. It'll already have the same number of dimensions, but that doesn't mean it's in the same embedding space. The embedding space of the concatenated tokens is different from the embedding space of like the sentence embedding. Essentially, we need this projection layer that can understand how to aggregate the information from from the attention heads. So this is embed dim to embed dim, and then drop out. Right. Right. So torch.cat along the last dimension. So we're going to say head x for head in self dot heads. Yep. So we're going to concatenate all those together. Then we're going to send it through the projection layer, then return the dropped out values. So it's right. This should now give us, this would recover our 512 dimensional embedding. So multi-head attention and heads. Wait a minute. Size should be 32 here. That'll give us for 8 heads. I mean, it could be whatever we want it to be. It doesn't matter, right? But I want it to line up with the rest of what we're doing. So actually, head size will be D divided by okay, that should work. Yep, we have our reclaimed, oh. Huh, okay, it's 64. Wait, I can't do math right now. Okay, it's 64. All right, so now we're gonna do transformer block. Well, no, first we need feed forward. I like to make this a separate class, same as my last implementation. Wait, we have multi-head attention. Yeah, we need to do, before we do the transformer block, we need to do feed forward. Forward. So I'm just going to return this straight away. I know what I want. I just want sequential. So yeah, I'll let you, yeah, so okay. Feed forward is going to be this, linear GLU, linear dropout. So linear, and remember, we're going up and then back down. So we're scaling up. I'm going to give it an MLP ratio, just like the PyTorch function has, the PyTorch transformer function has. So embed dim, going to be embed dim MLP ratio P dropout. From the paper, it's supposed to be 4. So embed dim MLP ratio times embed dim show you boom, we scale it back down, and then we drop out. Boom. That's gonna work. Should be same beat by T by D. Embedding MLP ratio 4. Yep, that works. Same shape and what we expect. Okay, now we're going to create our transformer block. Self ratio and heads. It's going to be a combination of all the fields from the classes before. P ratio 4, embed dim 512, and heads 8. Always got to call the super constructor. Let's do the forward. Transformer block. I think transformer block is a layer norm. Yeah, but okay, yeah, I remember. It's where it's not from the paper. The paper does post normalization. But everyone since then, since the release of the paper, has been doing pre normalization. So we need our multi-head attention. Okay, so just so you guys can see, transformer block. Oh, right. Layer norm, multi-head attention, layer norm, feed forward. And heads, bed dim, feed, drop out. Feed forward, P ratio, P. So we're going to do X is self.layer up X. And then we're going to do X. Remember, there's skip connections. So after the layer norm, we add the multi-head attention output to X as residual. So X plus self.multi-head attention X. And there's going to be a mask here. I need to make sure I pass that mask in, and I need to make sure multi-head attention accepts the mask. Heads, pretty sure accept mask. Let me run this again just to make sure it's, yeah, that's fine. Okay. Starting to get a bit of a headache. Okay, then we do layer norm again. Then we have another skip connection. It's our transformer block. Embed dimension and heads. MLP ratio. Okay. So we should get the same dimensional event, the same embeddings, which we did. Okay, so now our transformer is almost complete. So actually, our transformer is complete. So now let's go to our clip module and let's actually, so we can see we're calling the transformer modules here. Let's implement a vision transformer. So vision transformer takes in an image. Boom. So vision transformer here, patch embedding, transformer blocks, layer norm. Cool. Should be able to do that, no problem. So self dot patch embed patch embedding. Image size, channel, embed dim, patch size, P drop out. Self dot blocks, depth, blocks equals transformer. Let me just do this. And heads, dead dam, MLP ratio. Okay. And range depth. Okay, that's going to be the number of blocks. Depth is the number of blocks that we're creating this module list. That has all our transformers, right? So we just created our transformer blocks, and then we need a layer norm. Self.layer norm. Okay, now X is patch embedding, and then for a block, actually I can just make this a sequential, and then unpack this list here, and then I can just say access these self.blocks. Return self.layer norm X. Cool. So that's our vision transformer. Okay, so what about our text transformer? Text transformer. Okay. Super constructor. Let's put a skeleton for the forward. Okay. So text transformer is going to have, again, so we're taking in a list of token IDs. So we need to tokenize, or so we need to create token embeddings. So we need to grab those from an embedding lookup table. We need to add the positional embedding. And we're going to add the layers, the transformer blocks. And then we're going to have another layer norm. So embedding, positional embedding, transformer blocks, layer norm. Okay, cool. Shouldn't be a problem. Token embedding is going to be vocab size embedding. Cool. We're gonna have a lookup by vocab size, and it's gonna return an embedding of size 49408. That's by the clip tokenizer is going to give us, this is the output of the clip tokenizer. It's going to give us the vocab size, and then I think we need the end of string, end of string token ID. The end of string token ID is the one, is literally the token ID before the last, it's one of the, it's the second to last token ID. Gonna have depth in there too, because we're just gonna grab this right here. But we can't make this a sequential. We need to make it a module list, which means we need to remove that. And we have positional embedding. So let's clean this up first. Then image size, wait, sorry. Embedding dimension. Okay, parameter. Okay, so this is positional embeddings. Another, we're gonna have to broadcast it, right? So it's gonna be 1 by context window size. Again, I've covered this in the previous video before. In the first video, actually the very first video I made, where I just kind of coded Nano GPT, just like our Andre Karpathy did. So we have a context window size 77. That's clip standard context window size. So that's the maximum size that a token can be. Boom, embedding dimension. It's 8. MLP ratio 4. P dropout 1. Depth 6. I think I made it 6 up here too. Oh, I didn't give it any. Okay. Well, that's fine for now. Okay. I didn't check out. If main main. Okay, let's make this vision transformer. Oh, yeah, I guess I should have grabbed. Text transformer. Well, maybe I can just leave all the defaults. Well, wait, sorry. I'm gonna do vision transformer first. It's the whole reason I went to grab Okay, so I guess this doesn't have defaults, so 4, 3, 512, 32, 0.1, 6, 8, 4. Okay, now let's run this. Local variable x referenced before assignment. Yep. Okay. Boom. So not enough values to unpack. Oh, where are we? Okay, sure. Okay. 10 by 50 by 512. It looks like it did before previously, and based on some of the modules that we were running before, so that looks okay. Phone. Okay. Okay, it's working. Boom. Text transformer. Oh, what just happened? Token embedding. Okay. Block and self.block, send it through all the transformers. The reason why I needed to expand it out this time is because we'll have an attention mask. So mask and then self.layer norm x. Okay. Boom, that's, wait. Okay, it's not working. Expected tensor for argument. Token embedding. Oh, right. So, well, I need to do this either way. We need to make sure that we're only selecting up to T. So B, T, D. Tokens. Line 38. Tokens. Right, okay. So it should have the same error. Oh, yeah. I need to do size of it. B, T, E. Size of it. Is O. Oh, right. So we're not sending in a D dimension here. This is we're actually sending in just the token IDs, right? And then we're getting it from the lookup table. If we didn't have this, yeah, so just we're not sending in, yeah, we need to send in a tensor that's mirrors the shape of a batch with a list of token IDs. So this will work. No, it didn't work. Oh, also, I don't want to return this yet. I'm not done. Also, for that, I'm not returning layer norm. I want to return the class token. So I want to return everything from the batch and then the first element of all items in the batch, which is the class token. And then right, and then so this, yes, too many elements to unpack. So let's return this for now and see what we get. Okay, 10, 7, 5, 12. Yep, that's right. But we want to return the last token of every sequence. And we're going to train the model to make that token be the aggregate, to contain the aggregated information from the sequence. In order to do that, we need to get the EOS. That's why I made this EOS token. So EOS mask. So what we need to do, we need to make a mask. We need to make a mask that tells us where the EOS token is. So we're going to say tokens.eq self.EOS token. Okay. This gives us, right, so this will give us a Boolean. This will give us a 0 if it's equal to the EOS token, or a 1 if it's, or sorry, this will give us a Boolean if the token in that position is equal to the EOS token or not, right? So each token in your, so for every element in the batch, each list of tokens will have an EOS token that identifies the last position in the sentence. And if that's simply the end of the token vector, then it'll be the last position, right? Otherwise, if it's not, and we have padding afterwards, then the EOS token will mark the last position in that sequence. So now that we have a sequence of Booleans where true, right? So now we need to say EOS mask. So if the EOS token, right? So what if it goes to the max length of the token, the context window size, then it won't have an EOS token, right? And so we need to manually insert one, right? So we'll say EOS mask last position equals true. Then we'll say EOS position, EOS position will be, now we need to select, now we need to remove. So now if we identified where the token was before, right? But then we also added manually the EOS token to the end, right? A true for the end. then we need to remove that true, right? And just only use the properly identified EOS token. So we're going to say EOS mask dot, we're going to change it to int and then take the argmax of the last over the last, right? Yeah, over the last dimension. And then we're going to return. So now we need to index into X, okay? Now we need to index into X, which is of size B, T, D. And we need to cut off, we're going to index into, we're going to basically on this token dimension, we're going to use the mask to remove. So for the tokens that were padded to fit the rest of the context window size, we have this mask that identifies where the EOS token is, and we're only going to return a vector. We're only going to return the vector up to that point. So we're going to say torch.arange. So we need to select so for the batch side, this is going to select each element in the batch, and then for each element in the batch, we're going to select, right? We've returned argmax here, so we're going to pass in a list of indexes. So we're going to select every element in the batch, and then for every element in the batch, return up to the EOS position. Or sorry, return the EOS position. Sorry, yeah, let me backtrack that. I got mixed up. I was saying that we're returning up to the last token. We want to return the last token in the sequence, right? The sequence. So we need to create a mask sequence. Okay, that's what we're doing here. This should work. I always say that and then it never works. Oh yeah, this works. So, okay, now we're gonna make clip. Class clip. Okay. It's going to take an image, caption, mask. All right, so, okay, clip. We have the vision transformer and the text transformer. Now we need to have the projection layers, unit normalization, and then calculate the similarity score. Okay, so vision transformer. In size. In size, in channel, bed, dim, patch, size, P, dropout, depth, and heads. and has MLP ratio. Okay. I'm not organizing these fields. I'm just optimizing for speed right now. So self dot transformer text vocab size EOS token dim window size and heads E ratio E dropout text depth. Okay. Now we need the projection dimensions for the projection layer. It's gonna be embed dim projection dim vision projection, and then yeah, I think that's it. So okay. Feeling pretty fatigued. Let's finish this up. So, all right. Image embedding is going to be self. I'm going to project the output from vision encoder. And the text embedding, do the same thing. Transformer text caption. And this is also going to take in the mask, right? Should take in the mask. Yes, I did code that in there, but not for the vision. Good. Okay. So now, just to make this easier, I'm going to calculate for the batch. I'm going to calculate the logic. So I'm going to calculate the similarity matrix, and that's what I'm going to return. Instead of just calculating one similarity score, we need the matrix for, remember, for contrastive loss, we need to calculate, this, we need to use this matrix to calculate our loss. So this is just the cosine similarity, or in our case, the dot product between images along the rows and text along the columns. So say logits is I embed. Oh, right. I need the learnable temperature here when I'm calculating this similarity matrix. It's going to be a learnable parameter, so it's going to be sure parameter torch.ones. I'm going to so it's a single parameter. So it's a parameter, so I need to make it a tensor. I can't just pass in a number. I need to make it a tensor. So I'm saying torch.ones, right? And then I'm going to multiply it by a value. So 1 divided by well, yeah, okay. It'll be a hyperparameter. So I need to get the config. No, I need to, sorry. I need to pass that in here. Oh, temperature. Yep. Pretty sure that's right. So here I need to do embed. So now we're gonna do the cosine similarity, which because we've normalized. Oh, okay, I'm missing a step. So now I need to normalize. So embed receives f dot normalize. So this is unit normalization. Okay, now I'm gonna do embed. So because we've normalized the unit normalization, we can just take the dot product. So t embed dot t. So we're transposing. Right, this is gonna be the d, and this is gonna be b t d, where d is we'll call it proj_din, where even the image embedding that wait, no, sorry. Right, because we're returning the class token and we're returning the last embedding of each sentence demarcated by the EOS token. So we're removing removing that dimension, the t dimension here, and then we're sending it through the projection, which will give us our projection dimension. So now when we do transpose, let's just switch these two, and then we multiply by self.temperature. So this will scale the temperature. So this is gonna, right, it's a scalar value. So this is doing element-wise multiplication, and it's gonna scale our logits, which is gonna scale our softmax distribution. Okay, so I had some more, there's a couple of edits. One, this temperature needs to be .exp. I was wondering why my loss was so small last time. This needs to be, it's e raised to the power of the temperature. And also there's a normalization step I missed. Yeah, here you go. X. Yeah, those are the changes I wanted to make. So yeah, we'll keep going with the video. I'll insert this. All right, so now we're going to return the logits, embed, and the t-embed, because we can use these embeddings, now that they're in the same embedding space, we can use these embeddings in the diffusion process to condition the diffusion process. So that looks right. So missing arguments, clip in it, missing foot. Oh. Okay, yeah, okay, well, sure. How about, for time right now, how about I just give them default values? 3, 512, 32, 1, 6, 8, 4, 4, 9, 4, 0, 8, 4, 9, 4, 0, 7, 77, 6, projection dimension, we'll just leave it the same. 512 as the dimension, as the transformer dimension, temperature, leave it 0.07 for now. What do I want to make the temperature? I'll make the temperature, you can always change that. Remember, this is learnable, so I don't know. The model will choose what temperature is best. All right, so let's run this again. Caption, clip for, oh, wait. So image, caption, image, caption. We don't have a mask yet. I'll make the mask when I create the data set, or maybe when I collate the batch. So for right now, we'll leave that none. We're gonna make sure I'm passing it in. I'm passing it in. Logics, image embedding. I don't need those. Well, sure, why not? Shouldn't need to do that. Yeah, that looks right. That looks right. We change the projection dimension to 256. Yep, that looks right. Okay. So now let's do the last function, and then I'm gonna pause the video and take a break. So I'm pretty fatigued right now. Just make it a class. Okay. Okay, so we're we're going to say loss, contrastive loss, logits. It's going to take in the logits, and then going to print the loss. Okay. All right, so I'm going to say loss function is cross entropy loss. And then this is going to take in the logits. And we're going to say, okay, all right, so we have our logic, we have our similarity matrix. Now we need to create loss image to text and loss text to image, right? So, which is the cross entropy loss. Remember, this is supposed to be negative. Oh, I didn't upload the change. This is supposed to be negative. Cross entropy always has a negative here. Otherwise, any value you put into log that's less than 1 is going to end up negative. So you need to multiply by a negative here to make it positive. So your minimization actually minimizes a positive number. Otherwise, it'll end up. Yeah. Anyways, okay. So we have this similarity matrix. So let's create loss image to text. So we have the similarity matrix, and we know from our previous videos how cross entropy loss works. We pass in logits, and it normalizes the logits for us, right? Which it's more stable than using cross entropy. Anyways, there's another function you can use that where you pass in the softmax. You do the softmax manually, and you pass it in, but from all accounts, the cross entropy, the cross entropy class or the function cross entropy with logits is supposedly better. For reasons I don't know, I haven't dug into that yet. Okay, so loss image to text. We already know this is, we pass in a logits matrix, and we already know that it knows how to handle this. So loss image to text. Image to text. Let's call it image to text. Oh, okay. It's gonna be logits, right? Right, so it needs logits and it needs labels, right? It needs labels that, right? So whatever label you pass in it's going to return the normalized logits for that position in the tensor, right? So we need labels, right? We don't really have like standard supervised labels like in the very conventional sense. Right, but our labels are, we know that these are the matching pairs. We know that these are the positives, and that's what we want it to return. So we'll just index along the diagonal, right? So we'll say labels is equal to torch.arange. Sorry, logits dot size of its first. So this is the batch dimension, right? And then make sure we need to send it to the same device, and then boom. So this is going to count from 0 all the way up to, right? This is a list. This is a tensor that counts from 0 to the size of the batch, which allows us to index along the diagonal. And it's already normalized by default. It always normalizes row-wise, the cross entropy loss function. So it does that normalization inside the function, right? And so to get text to image, we do the exact same thing, right? Except we just say logits.transpose. And now that switches. So I'm representing it symbolically different here. I'm showing you we're normalizing along the columns. That's how I'm doing this indexing. That's how I'm doing this. That's how I created these functions P and Q. I created the function Q such that I'm doing the indexing in the denominator that it normalizes along, it normalizes column-wise, right? But in practice, when we use this cross-entropy loss function and it does the normalization inside, right? It's just, we just do transpose and it's really neat and fast. And then we just return the average. Loss image to text plus loss text to image, and then we divide by 2. Boom. 2.3. That looks reasonable. It looks about what we'd expect for initializing tensors to be 0. Which I'll go over the math of what we might expect our loss to be for a model that's at random, given, you know, yeah, I'll go over that, given we're using the log function. So, okay, I'm gonna pause the video here. I'm tired, I need to take a break, maybe drink some coffee, maybe eat some food and re-energize myself. So let's pause the video. I think I might actually stop the video here. I paused it and then I was like, you know what? I've been coding for a while. I don't know, maybe I'll stop the video, edit this, publish it, and then the next video will be a training run. I think I'll do that. I think this code is right, just based on the shape of the tensors. And then if I have any issues, so yeah, let's just finish this up. So, okay, so I paused the video and then I thought about it and I was like, you know what, let's just finish this up. I'm pretty tired. I coded the entire clip and then I'll make a new video maybe tonight of me doing the training run. So I'm pretty sure this is right. All the tensor shapes look correct. So we have this clip module, and we have this transformers module, and then we'll have a train module. I have some skeleton code here, and we'll fill this out. I'll code up the set, custom data set, custom collator, and we'll do a training run. Yeah, so thanks for watching. Later.